For centuries, mathematicians assumed that a shape like a circle or a sphere had only one possible smooth structure, a unique way to draw curves on it without sharp edges. John Milnor proved them all wrong. He discovered that there are many different types of spheres hiding in higher dimensions. He focused on the 7-dimensional sphere, a shape impossible to visualize but essential in mathematics. Milnor showed that this 7-dimensional sphere doesn't just have one, but an incredible 28 different differential structures. Think of it as discovering 28 different ways to define smoothness on the exact same geometric object. He called them exotic spheres. This single result revealed a hidden complexity in even the simplest shapes and gave birth to an entirely new field, differential topology. For this discovery, he was awarded the Fields Medal in 1962, and his work reshaped not only topology, but the philosophy of mathematics itself. John Milnor was born in Orange, New Jersey, a prodigy with a quiet intensity. He entered Princeton University at just 16, a place that would remain his intellectual home for decades. Under the mentorship of the great John Nash and the legendary Alonzo Church, Milnor absorbed ideas from both mathematics and logic, worlds that rarely met. By his early 20s, he was already producing results that astonished senior mathematicians. He was fascinated by the shapes and structures that live beyond our perception, not just in 3 dimensions, but in 4, 5, or even 7. John Milnor's work on exotic 7 spheres is one of the most counterintuitive discoveries in modern mathematics. To understand it, we need to separate 2 ideas that were once thought to be the same: homomorphism and diffeomorphism. Think of a rubber duck. Topology, or homeomorphism, studies shapes based only on their gross flexible properties, how they can be stretched or twisted without tearing. Your rubber duck is homeomorphic to a sphere. It's one piece with no holes, so theoretically, you could mold it into a perfect smooth sphere. From a topologist's perspective, the duck is a sphere. Differential topology, or diffeomorphism, this studies shapes based on smoothness, how curves, slopes, and coordinates behave across the surface. Now imagine 2 ducks. The standard sphere duck, it's perfectly smooth, high gloss. Draw any line on it, and all the slopes and derivatives behave exactly as expected. The exotic sphere duck, it has the same overall shape, but with a subtle, invisible texture. To a normal topological eye, it looks identical. But any tool that measures smoothness, the derivatives, the local curves, immediately notices a difference. Milnor discovered that in 7 dimensions, there are 28 distinct smooth structures on a sphere. 1 is the standard sphere, and 27 are exotic, each topologically identical but with a different smoothness, like subtly textured rubber ducks. But why 7 dimensions? Because in 1, 2, and 3 dimensions, a sphere's smooth structure is unique. dimension 4 still remains a mystery. But dimension 7 is the first place where topology and smoothness truly part ways, showing that even something as simple as a sphere can hide immense complexity. Milnor revealed 28 parallel universes of spheres, all topologically the same, yet each with its own hidden twist. A sphere is no longer just a sphere. It's a doorway into dimensions we can't visualize, with structure and smoothness richer than anyone had imagined. His paper, On Manifolds Homeomorphic to the Seven Sphere, 1956, became a landmark in modern topology and earned him the Fields Medal 6 years later in 1962.
John Milnor didn't just revolutionize geometry, he also reshaped algebra with his work in algebraic K-theory. Algebraic K-theory is about understanding how algebraic structures like rings, fields, and vector spaces can be classified and related. At its heart, algebraic K-theory asks, given a field or algebraic system, what are its fundamental building blocks and how do they interact? Before Milnor, the field was scattered and abstract. He introduced Milnor K-theory, a concrete framework that lets mathematicians capture the deep, hidden structure of fields in a computable way. Milnor's K-theory connects algebraic structures with geometric objects, like in the study of quadratic forms or vector bundles. It laid the groundwork for advanced theories, including motivic cohomology, algebraic cycles, and number theory.
String theory explores the tiniest threads of the universe, and Milnor's exotic seven spheres fit right in. These spheres look identical, but each has a hidden twist, a smooth structure that changes how you move through them. His work in K-theory maps the hidden structure of fields, giving mathematicians tools to tackle number theory, algebraic geometry, and cohomology, while even influencing cryptography and coding theory. Meanwhile, his topology techniques are now used in computer science to analyze and visualize complex, high-dimensional data sets, uncovering patterns that were previously invisible.
John Milnor is one of only 4 mathematicians in history to have won the 3 highest honors in the field: the Fields Medal, the Wolf Prize, and the Abel Prize. This unparalleled achievement is the signature of Milnor's extraordinary legacy. He didn't just master existing mathematics, he fundamentally reshaped it, uniting geometry, topology, and algebra through a series of revolutionary discoveries. Milnor was a prodigy of almost unbelievable ease. He was an undergraduate at Princeton when his first paper was published, and his early career was marked by a quiet, almost playful genius. When asked why he chose mathematics, he famously replied, "Because to me was easier than other subjects. I'm very lazy, you see. I do what's easiest for me." Even today, his discoveries continue to inspire new generations, teaching us that beauty in mathematics lies not in certainty, but in uncovering the hidden dimensions of the familiar world. John Milnor didn't just study shapes. He revealed the secret life of space itself.
This is Awards, where the world's greatest minds live forever. Don't just watch history. Be inspired by it.
Thanks for being with Awards. Subscribe to know more about international award winners and unsung heroes behind peace, science, and humanity.